So we have this puzzle, or physicists had this puzzle in the 1890s, what to do with something like the Michelson-Morley result, the null result, that showed that a motion through the ether could not be detected, even though it should be detectable, especially when you compare it to the results of things like stellar aberration, where it said clearly the ether could not be dragged, which was one possible solution to the Michelson-Morley experiment that said, okay, we're not detecting the motion of the Earth through the ether as the Earth revolves around the sun. Maybe it's because the ether in the vicinity of the Earth gets dragged along, and therefore we don't feel that either wind or either breeze, as it were, or our experiments do not detect it. Yet other results, like stellar aberration, said, no, the ether can't be dragged along by the Earth if you're going to get the correct results for things like that. So it was a real puzzle. But there were some solutions that were proffered for it. A British physicist, G.F. Fitzgerald, really just came up with an idea that, in the Michelson-Morley experiment, you have light traveling one way, sort of the headwind, tailwind with the ether wind supposedly, and then going perpendicular, where the ether wind would be crosswind to it. And there should be a time difference between them, because the headwind, tailwind case should take a little bit longer than the crosswind case. So what he hypothesized was, he just sort of had the idea that, we're dealing with the ether, the luminiferous ether. Clearly there's some electromagnetic effects perhaps going on. Matter itself was thought to be composed of perhaps electrical particles. The electron actually hadn't quite been discovered at this point, but the idea was in the air that certainly electromagnetic quantities could explain perhaps the very essence, the constitution of matter. So if matter itself was electromagnetic in nature, the atoms involved and so on and so forth, perhaps there was an effect as matter, in this case the Michelson-Morley apparatus, traveled through the ether against it, that it got compressed a little bit. Just the very nature, sort of a drag effect in a sense, not like the ether drag we talked about before, but just a compression effect. If it's going straight through the ether and going crossways, you wouldn't have that compression effect. So one leg of the Michelson-Morley apparatus would get compressed just slightly, and the other leg wouldn't, and it'd be just enough to make up that time difference, so that the light beam going this way with the headwind-tailwind case would actually have slightly less distance to travel than you would expect compared to the crosswind case, and that slight difference in the distance traveled would make up for the fact that it's actually a little bit slower. So even though the idea would be, yes, it is slower, but the time traveled is the same because the distance gets compressed a little bit. And this is became known as the Lorentz contraction, because Fitzgerald published it in the American journal Science. He just sent a letter off, actually. It wasn't a full publication. Sent a letter off to the American journal Science, which was very new at the time and hardly anyone ever read. He wasn't even sure it had been published. Really, he was on to other things. A few years after this, in the mid-1890s, Lorentz, who we've mentioned before, was developing a full-fledged theory and extending Maxwell's theory and really puzzling over the Michelson-Morley result, and had a similar idea. And then he mathematized it and introduced it into his theory. He later found out that Fitzgerald had actually had this idea a few years before and had sort of published it. And Lorentz, just being the kind of person he was, gave credit to Fitzgerald, and therefore became known often as the Lorentz-Fitzgerald contraction. So we talk about the Lorentz-Fitzgerald contraction. And again, the idea here is that if you have any material object going against the ether, or just traveling through the ether in a longitudinal direction, in the direction of travel here, it'd be compressed slightly. So if it's a spherical object, it becomes sort of slight ellipsoid. Not so much that you could really notice it unless you're doing very precise experiments, but that's exactly what Michelson-Morley was. It's a very precise experiment, and therefore the idea was that this effect would show up in the Michelson-Morley experiment, shorten the distance slightly, so that even though the travel time should be longer that way. The distance was shortened a little bit, and so the travel time equals out whichever way you're going on the Michelson-Morley apparatus, and therefore you get this null effect. You don't see any effect of the ether wind. So that is, the ether wind is actually there, but we don't notice it because of this contraction effect. That was the idea of the Lorentz-Fitzgerald contraction. Henri Poincaré also took some of Lorentz's ideas, 1895 and following, over the next 10 years, and they both developed them further. Both of them also played with ideas of that time itself might be elastic, sort of like length is a little bit elastic here. It can change a little bit, the physical length of something. If it's moving against the ether, can change. They had the idea that maybe time is involved as well, because to make things work out in the full context of the theory, if length is changing a little bit, then there seemed to be some need for time to change. Now, the ideas they had were more mathematical constructs within the theory. They weren't necessarily saying these are actually physical changes in time. Time, they would say, really is absolute. It still goes along just for everybody the same way. But there were hints of perhaps a change in how we viewed time, and that maybe time wasn't as absolute as everybody thought it was in the work of Lorentz and Poincaré. And so that's where then Einstein enters the scene and comes at it from a very different perspective. All of Lorentz, Poincaré, Fitzgerald, they were working within the context of how do you construct a model of the ether? How do you explain these experimental results? The null result of Michelson-Morley, the result from stellar aberration, other things like that. Einstein really came at it from a more theoretical perspective. In fact, was a debate really, about was there any effect of the Michelson-Morley experiment on Einstein's thinking at this point in time? And we're not sure. In later years, about 15, 20 years later, he actually mentioned the Michelson-Morley experiment, that it did have an influence on his thinking, the null result. But at the time, in his actual paper, he doesn't cite it specifically. He clearly was aware of it, and a number of other experiments like it in terms of investigating the properties of the ether, because we know he read an article about 1899 or so where it was mentioned among a number of other of these experiments. But the evidence that it really had a decisive influence at the time is lacking. He seemed to be bothered more by, as we mentioned previously, these theoretical asymmetries in electromagnetic theory versus the principle of relativity. So it's really a question that we can't quite answer, but the evidence seems to be pointing to the fact that the Michelson-Morley experiment, even though many others were very worried about it, didn't bother Einstein as much at that point. And this actually is important in terms of sometimes people point to how should we do science? Is there the one correct way to do science? And the example of the Michelson-Morley experiment sometimes is pointed to say you should do experiments first, see what the results are, and then build theories from that. And they would then point to, see, that's exactly what Einstein did. He took the Michelson-Morley result, built his theory on that, when in actual fact he almost did the opposite. We talked about the two postulates. He really took results from electromagnetic theory and the principle of relativity from physical theory and built this theory on those two postulates, and then later on compared it to experiments. So philosophers of science and others argue about these things. But the evidence, historical evidence, seems to say that Einstein did not, we should say the Michelson-Morley experiment did not have a decisive influence on Einstein in terms of his June 1905 paper on the special theory of relativity. Well, what was Einstein's ethereal solution? So the solutions, Fitzgerald, Lorentz, Poincaré, they're still working within the context of the ether, figuring that maybe matter itself is modified as it travels through the ether, and maybe even time, the nature of time itself is modified, at least in a mathematical sense in terms of the theory. What did Einstein come up with? Well, we've talked about his two principles or two postulates. So let's go back to them now that we have a better understanding, especially of how waves work and how light works, hopefully. And let's think about the principle of light constancy. one of the two postulates, the other one, of course, being the principle of relativity. And we want to look at three cases here, because what Einstein, his great insight was to say, yes, the principle of light constant, that's true. Good evidence for it, both from theory and then actually later from experiment as well. We'll remind ourselves about that in a second. Principle of relativity, that's true also. They seem to be in conflict, but actually we'll take them both as true and then see what the implications are and the results we get. And so what are those results? Well, the principle of light constancy, remember, essentially says that if light is a wave, an electromagnetic wave, and if you have a moving source of a wave, in our example we used water waves and a paddle device, if that paddle device, which is generating the waves, the source of the waves, is moving through the medium, moving through the water, it does not change the velocity of the waves coming off that paddle device. Okay? The velocity of waves depends on the medium in this case. It will still flow away with whatever velocity, whether the source is stationary or not. And so let's imagine, let's go back to Alice here. Let's say here's Alice. And we're going to put the ether in here at first. So we'll imagine something roughly like this, okay, for the background of the ether there. So she's sort of standing on imagine a floor or something like that, or just the context of the ether around her. That's what I was trying to draw here to indicate that. And over here we have a light source. And let's get, so it's generating a light beam that is going to travel past Alice here, or Bob, or whoever we want, watching it there, observing it there. So if everything is stationary here, Alice will just measure this as velocity c. Okay? Nothing too strange about that. It's just the velocity of light going by, nothing in motion. Okay, so that's our first case. Now let's say, though, what happens if we put our light source in motion? Okay, so this is, again, like our paddle device. This is the source of the waves. We're going to put it in motion. We're assuming that ether exists here. That's our medium. So if we do that, if we say this is moving now with velocity v, Alice is still standing over there and has some device where she can measure the speed of the light, the velocity of the light going by. Based on the principle of light constancy, or really you could say wave constancy, that the speed of the wave in this case is not affected. Moving source does not affect the speed of the wave. In other words, if I move my light source, say just a fancy flashlight here that's generating the light beam going by, if that's moving at some velocity v, the velocity that Alice sees for the light wave will not be c plus v, it will still just be c. The velocity of light, again, presumed moving through the ether. Okay? So that's that case, right? And again, it's standard, nothing strange there. But now what Einstein essentially said is, let's apply the principle of relativity to this case. Because we're assuming this is true, perfectly fine here, but we're also assuming the principle of relativity is true. And so what the principle of relativity would say is that this case here, where the light source is in motion toward Alice, is the same thing as, let's just put an X through here for a minute to remind ourselves that was there a minute ago. What if we put Alice in motion this way? Okay? Toward the light source. So now the light source is stationary. Alice, if the ether exists, is moving through the ether toward the light source. And essentially, in that case, well, first of all, note that these two cases should be equivalent. Okay? That if the principle of relativity is true, we shouldn't be able to tell the two cases from each other. That whether Alice is moving toward the light source or the light source is moving toward Alice should be the same thing. We can't tell the difference. It goes back to the coil and magnet, that the example Einstein used at the beginning of his paper on the special theory of relativity. They should be equivalent situations. But let's think about this a minute in the context of the ether. That would say then that now Alice is moving through the ether. So from her perspective, there's the moving medium involved. Remember we talked about how when you move the actual medium itself and you have a wave going through it, then that speeds things up. That the speed of the wave to an outside observer will seem to be going faster because the medium is moving and then the wave itself through the medium is moving, so it carries it all along. You get an increase in speed. But what Einstein is saying is, if the principle of relativity is true here, both these cases should be equivalent. That if the light source is moving toward Alice, and Alice is stationary, by the principle of light constancy, the velocity of light is still c. Nothing changes. But if we switch it and have Alice moving toward the light source, it should be an equivalent situation. The normal theory of waves would say, no, now we add some velocity to this light. Einstein says, no, we're going to take the principle of relativity as true. There's good reasons, theoretical and experimental, to accept that. And so even though it seems like there's a contradiction here, we will assume there isn't. And therefore, this situation, Alice will still see the speed of light to be c. And in fact, the general conclusion is, no matter how an observer is moving with respect to a light source or a light beam going by, therefore it will always be c. It will never be c plus v in any given situation, because principle of light constancy is true. If the light source is moving that way, it's c. Therefore, by the principle of relativity, if you have Alice this stationary and Alice moving this way, which is equivalent, if principle of relativity is true, you can't tell the difference between those two situations. And therefore, in that case, too, Alice will still see it be c, not c plus v. And what this means is, Einstein's conclusion was that the either was superfluous. And if you looked at his paper, he states it almost right at the very beginning, first page or two of the paper. He says, the results of this paper, or words to that effect, will show that the concept of the either is superfluous. And then he developed some of the implications of that, which we will be looking at starting next week. But it's almost a throwaway line there. Well, this just shows that either is superfluous. And the response of many people would be going, huh? What are you talking about? We need the either. How do you explain how light waves work without the either? People like Lorentz and Poincaré had been working for years on this and developed very sophisticated theories, and you just want to throw that out? This 26-year-old Einstein? And yet, by going back to the sort of basic foundations of physics, how we think about length and time, based on these two postulates, Einstein gradually won people over. Later in the course, we'll talk about sort of what happened after 1905, because it wasn't an immediate acceptance of the theory, but it did take a while. But eventually, people were won over to sort of the Einsteinian point of view in this. So, again, principle of light constancy plus the principle of relativity. The conclusion Einstein drew is that c, the velocity of light, is a constant no matter how you're moving. Whether you're moving toward the beam or away from the beam or sideways to the beam or however the beam is moving, you will always measure the speed of light as c. And again, that's going to have some very interesting and strange consequences, which we'll get into starting next week.